Welcome back to our quantum information theory lecture. Let me briefly recall what we did the last time. So in our last lecture we started with a brief introduction into entanglement theory. And in particular we started with considering a completely uncorrelated state, namely a product state, so a bipartite product state. And then we asked which transformation cannot lead to more than classical correlations, right? And there we came up, or we found that there is the set of local operations in classical communication. So we abbreviate this by LOCC, and we found that under LOCC operations we cannot, so given such a product state, we cannot generate entanglement. And we also argued that given any state, entanglement must be non-increasing under these LOCC operations, right? And we did formalize how such LOCC operations look like, and we found that if we have such a product state without any correlations, by LOCC we can reach every separable state. And we then defined an entangled state as a state which is non-separable. Okay, this was how we defined entangled states. And our aim now is to quantify entanglement, right? And we started going into this direction by considering two states, say rho and sigma. And suppose that I'm given rho, and by some LOCC I can transform to sigma, right? In this case, we know that rho must be at least as entangled as sigma. So rho must be at least as entangled as sigma. Then we also considered the following instance. Let me say we have some rho, and via LOCC we can transform rho to sigma. However, via LOCC we can also transform sigma back to rho, right? And if you take this statement serious, then this means that rho and sigma must have the same amount of entanglement, right? And we also considered those operations for which this holds. Namely, these are the so-called local unitary operations. Let me abbreviate this by LU. So these are local unitary operations. And we then called those states which are connected by local unitary operations as locally unitary equivalent. So yeah, local unitarily equivalent. Okay. So this was then. The last part of our last lecture was the definition of these local unitary equivalent states. So hence, or select this. So we have then defined this, that rho and sigma are local unitary equivalent. Okay, but we now continue in this direction. What we do now is, for simplicity, we restrict to pure states. Okay, and we ask, given a pure state psi, how can I decide whether I can go from psi to phi via LOCC transformations? Okay, so under which conditions can I do this? That's what we're going to do now. And we do, for simplicity, now consider pure states. So for simplicity, let's consider bipartite pure states. Namely psi, which is an element of Hilbert's decomposite system HA and HB. And in order to decide now under which conditions I can transform psi to phi, let me first recall the so-called Schmidt decomposition that we considered in the very beginning of the lecture. Okay? So first, recall the Schmidt decomposition. Which tells us that we can write this psi as follows, namely as psi equal to sum over j, and then we have the square root of lambda psi j, and then some vectors v psi j and w psi j, where these lambdas over the square root of lambda psi j are the Schmidt decompositions, and remember that they are greater or equal to 0. Sorry, are the Schmidt coefficients? Yeah. Of psi, and then these vectors, namely this vectors v psi j, the whole set, and the vectors w psi j, so the whole set is, they form an orthonormal basis of the Hilbert space A and B. This and this form an ON basis of HA and HB respectively. Okay, we can now write down this state phi in its Schmidt decomposition. So similar, we can write this vector phi in this form. So we sum over those Schmidt coefficients, lambda phi j, and we have now these basis states, let me call them v phi j and w phi j. Okay, so the only thing that we did is we used the Schmidt decomposition and wrote down this state psi and phi in the Schmidt form. Well, and now what we know is that under local unitary transformations, I don't change the entanglement, right? So what we can do now is we can find local unitary transformations such that these basis states, v psi j and w psi j, are equal to these basis states v phi j, v phi, and w phi j, right? So we can find local unitary transformations such that the state psi reads as follows. So I sum over the Schmidt coefficients lambda psi j, and then I have the basis v j and w j. So we simply did a basis transformation of these respective systems, right? And we also perform a basis transformation for phi. Write it in this form, phi j, and then we have v j and w j. So we have now the same basis states for psi and for phi, and we can do this transformation without changing the entanglement of phi and psi. We can find local unitary transformations such that this, hence, the entanglement, or the amount of entanglement, psi, and phi didn't change. Well, and now we can take a look at these two states, and we see that they only differ by their Schmidt coefficients, right? Meaning that in order to decide whether we can transform psi to phi via LOCC, this must be somehow explained by their Schmidt coefficients, right? Because the states only differ by Schmidt coefficients. So that is so deciding whether we can transform psi to phi via LOCC can only depend on the Schmidt coefficients of psi and phi. So to this end, let me now list all Schmidt coefficients by a vector. So to compare these Schmidt coefficients, let's introduce the vector lambda psi j, which is simply a vector which contains the squared Schmidt coefficients, lambda psi 1 to lambda psi d. So let's introduce this vector, which contains all squared Schmidt coefficients. And let's denote by this lambda psi, and then as a superscript we have an error. Let's denote by this the list of squared Schmidt coefficients now in decreasing order, or the vector. Let's denote by this the vector of squared Schmidt coefficients. In decreasing order. This means that lambda psi 1 and then arrow downwards is greater equal to lambda psi 2 and so on, greater equal to lambda psi d. Okay, so far we did nothing else than taking all of these squared Schmidt coefficients and then ordering them such that in decreasing order. And the same we do similar for phi. Similarly, for the state phi, we get the vector lambda phi. Okay? And as we will see now, the question whether we can transform psi to phi via LOCC can be answered by the so-called majorization. Okay? And this is, so therefore let me first define this majorization. So as we will see in a bit, the answer of our question can be obtained by via majorization. So what is majorization? I guess you didn't hear about this before. It's simply a way how to compare two vectors. So let's define this. It's definition 3.22. So given two vectors, say x and y, which live in a real vector space of dimension, let's say dimension d, we say that the vector x is majorized by y. You write this as follows, so written x and then this symbol y. If the sum over from j equals 1 to k, and then we sum those elements of the vector x j is smaller or equal to sum j equals 1 to k yj, and we sum over, as here we use the vector with the elements in decreasing order. So if this holds for all k equals 1 to d, so note that the sum is running from 1 to k, right? And there is, so to say, there are d different inequalities. So this statement contains d different inequalities, right? Because k can run from 1 to d, and this inequality must hold for all k equals 1 to d. However, we also require that we have an equality if k is equal to d. So with equality, instead of inequality, when k is equal to d. Okay, so this is definition of the majorization, and we now use this way of comparing two vectors in order to decide whether we can transform psi to phi. And we can decide this by the majorization of the corresponding Schmidt coefficients. Okay, so this is now the following theorem. Theorem 3.25. It says that any bipartite pure state psi can be transformed to another pure state phi with certainty via LOCC if and only if this vector of squared Schmidt coefficients lambda psi is majorized by the vector of squared Schmidt coefficients lambda phi. Okay, so let's go through it again. What we did is we asked whether we can transform psi to phi via LOCC. Okay? The first thing that we used is the Schmidt decomposition, and we wrote down the Schmidt decomposition of these two states and then used local unitary transformations to transform the Schmidt form of these states into the same basis. This we can do, and by only using local unitary transformations which do not change the entanglement of those states, right? Then we see that they only differ by their Schmidt coefficients, meaning that deciding whether we can transform from psi to phi can only depend on this Schmidt coefficients. We then took, or we defined a vector which contains all those squared Schmidt coefficients. And what we found by the theorem is that if we compare this vector via the majorization, we can decide whether we can transform it or not, right? So if this vector of squared Schmidt coefficients of psi is majorized by the vector for phi, then we can do this transformation. Okay, if it's not the case, then we cannot do it. Okay, that's an if and only if condition in this theorem. And the theorem has now immediate consequences. And I'd like to write them down as some remarks. So the first consequence is that there are so-called maximally entangled states. So if you take a look at this condition here for majorization, right? If I have a state whose squared Schmidt coefficients are given by 1 over the dimension of the Hilbert space. So meaning 1 over the dimension of the smaller Hilbert space of HA or HB, right? Because the Schmidt decomposition, I think we don't have it on the blackboard anymore, but remember that the Schmidt decomposition has D terms, where D is the minimum of either Hilbert space dimension A or B, right? So it can have at most D terms. And if you take a look here, then I find that if a vector whose Schmidt decompositions are all 1 over D, whose squared Schmidt coefficients are all 1 over D, is majorized by every other vector. And this means that such a state with this Schmidt decomposition must be a maximally entangled state. Because from this state we can go via LOCC to all other states. Okay, so let's write this down as remarks. First is from the theorem, we directly infer that there are so-called maximally entangled states and those must be unitary or local unitarily equivalent to the following state, namely to psi max given by 1 over square root of d, and then the sum over j. So with d being the minimum of dimension dA, dB, and this dimension dA respectively d is the dimension of the Hilbert space HA respectively B. Okay? So this is what I just said. We have a maximally entangled state. In this case, all the squared Schmidt coefficients are 1 over d. Right? And if you take a look at this condition here for the majorization, if you have here 1 over d, then you find that this one is majorized by all other possible vectors of squared Schmidt coefficients, and hence it must be maximally entangled. Because from this state we can go via LOCC to all other states. So hence, any pure state phi can be generated with certainty from this maximally entangled state via LOCC. Okay, now the second remark. The second remark is as follows. You know already maximally entangled states in the case of a bipartite system of qubits, right? So if d is equal to 2, then we have, which is the case if you have a bipartite qubit system, then you know those maximally entangled states, namely the so-called Bell states, right? And those Bell states are local unitarily equivalent. So you can transform from one Bell state to another Bell state via local unitary operations, and meaning that all of them are maximally entangled. Okay, so for a bipartite system, of 2 qubits, for which the dimension d is equal to 2. So this equation 3 was that the Bell states which we defined in the very beginning of the lecture, so and which are local unitarily equivalent they are maximally entangled. So you possibly remember that sometimes in the lecture I already mentioned that the Bell states are maximally entangled states for 2 qubits, right? And now we have quantified this. Okay. And then a second remark, which is possibly not so easy to see for the first time, but we're going to do an example in a bit, namely that by this theorem, it's such that there exist states which are incomparable, meaning that neither psi is majorized by phi, nor is phi majorized by psi. Okay? Meaning that there are states which cannot be transformed into each other in any direction via LOCC. And we call those states incomparable. Okay. So as a direct consequence, of theorem 325, they exist, or they are incomparable states. This means that pairs of states such that neither can be converted with certainty into the other via LOCC. Hence, we cannot tell which state is more entangled. Than the other. Okay, I mentioned where you can find the proof of the theorem, right? So we're not proving it here, but you can, for example, find this in the book from Nielsen and Huang. So for the proof, see, I think it's page 576 in the book by Nielsen and Huang. Okay, so we continue now with an example of such incomparable states, right? So it's possibly hard to see it from this definition. So I'm gonna state now 2 states which are incomparable, and we're gonna check this by this majorization criterion. Okay. So unfortunately, I have to erase this now. But remember this criterion that for the majorization, what we take a look at is the sum of the vector of squared Schmidt coefficients in decreasing order. Sorry. And remember that we have to take a look at all sums. So these are the different inequalities which you have to check. So let's do an example. Consider the Hilbert space H. So say we have two systems of dimension 3 such that D is equal to 3. So indeed we have to go to 3 in order to see such incomparable states, so above 2. And consider the following states. And psi equal to the square root of 0.4, 0, 0, plus the square root of 0.411, plus the square root of 0.222, and then phi is equal to 0.4800 plus 0.2611 plus 0.2622. So now we can write down these vectors of the squared Schmidt coefficients, so for which now lambda psi in decreasing order is given by 0.4, 0.4, and 0.2. Okay, so those are the Schmidt coefficients, and we take now the squared Schmidt coefficients. Okay, and for phi we get this vector lambda phi in decreasing order, which is 0.48, then 0.26, and 0.26. So let's check now whether lambda psi is majorized by lambda phi or vice versa. So if you remember those conditions, so the first thing is what we calculate is the sum from j equals 1 to 1 of lambda psi j. Okay, so this is simply the first entry here, which is 0.4. And we also calculate the sum now from j equals 1 to 1 of lambda phi, which is the first entry, it's 0.48. And we see that 0.4 is smaller 0.48. Okay? And now we simply increase the upper bound of the sum from 1 to 2. So this was the k in our theorem. And we said that there must be the same inequality for all k's, right? And for if k is equal to d, there must be an equality. This was the condition for majorization. Now we simply go from k equals 1 to k equals 2. So we have on the left-hand side the sum from j equals 1 to 2, and then lambda, it must be j, lambda psi j, which is, okay, this is simply a sum of the first two entries of this vector, which is 0.4 plus 0.4, gives 0.8. And then here we have the sum from j equals 1 to 2, and then lambda phi j. The first two entries here, which gives us 0.74. And now we see that we have here a greater. Right? From this we can directly see that they are incomparable. However, let's also calculate the last one, which is from 1 to 3, lambda j. And this one is 1. And the reason is that we consider normalized states. Right? So we have indeed this equality. If you compare the Schmidt coefficients for k is equal to d, simply because we are considering normalized states. Right? But the fact that we have here a greater sign, here a smaller sign, tells us that those states are incomparable, meaning that we cannot transform psi to phi with certainty via LOCC, and also not vice versa. Okay, I think we're going to do a break now. And what we do after the break is we're going to see how it looks like, we do an example of transforming a state to another via LOCC, right? Because so far the theorem that we stated only tells us whether it's possible or not, right? But no one ever told us how it works. Well, and in order that you can see how this works, at least for one example, we do an example. And then what we do is we take a Bell state, so a maximally entangled state of 2 qubits, and then we transform to any other 2-qubit state. Okay, so let's do this in 10 minutes after the break. Okay, let's continue with the lecture. We are now doing an example from which we see how we can transform via LOCC from a Bell state to any other 2-qubit state. Okay, so in this example, we use the Majorization criterion. Or say differently, we now come up with a LOCC protocol between Alice and Bob. So there's Alice, which is in possession of the system A, described by the Hilbert space HA. And she's doing something on her state. And then she communicates with Bob via classical communication. And then Bob, which is in possession of system HB, also performs some operation. So they share a common state rho, so which is a bipartite state. Or say we say that we consider this maximally entangled state psi, which is equal to 1/2, then 0, 0, plus 1, 1. And then Alice performs some operation, which we describe by a quantum operation E on this state psi. And then she sends the outcome J to Bob, who then performs a unitary operation. So let's call this E Alice and then E Bob on the state psi, depending on this on the message of Alice, right? And what we then end up with is a state. We aim for the state phi given by square root lambda 1, 0, 0 plus square root lambda 2, 1, 1. Okay? Now you see we write this down in the Schmidt decomposition form. And since we leave lambda 1 and lambda 2 open, we can generate via this protocol and local unitary transformations any bipartite state of 2 qubits, right? So if we can find such a LOCC protocol which gives this state, then together with local unitary transformations, we can generate every 2-qubit state from this maximally entangled Bell state. Okay. So suppose we want to transform this state psi via LOCC into the state phi. And then we know that this must be doable. Since psi is a maximally entangled state, meaning that lambda psi is majorized by lambda phi. Okay, so it must be doable. Now, consider the following transformation. So suppose that Alice first measures her qubit. According to the following map. So according to the map E1, E2, we have two measurement operators, so two operation elements. With operation elements E1 equal to lambda 1, 0, 0 plus square root lambda 2, 1, 1. And the operation element E2 is square root of lambda 1. And then with 0, 1 plus square root of lambda 2, 1, 0. And you can easily convince yourself that these operation elements satisfy the completeness equation, namely that sum over j e j dagger e j is equal to the identity. Okay, so if you don't see it directly, then do a short calculation, and you will see that this holds. Meaning that this set of operation elements describe us now a quantum operation, namely a trace-preserving quantum operation, which Alice performs, and then she does a measurement corresponding to this operation elements, and then sends the outcome to Bob. Okay. So suppose that Alice sends the outcome j, which can be either 1 or 2, right? Because we have two operation elements. So she does this measurement, and then she gets either 1 or 2, and sends this outcome j to Bob. Via classical communication. To Bob, who then performs conditioned on this j. The unitary transformation let's call this fj1 on his qubit where those unitaries are given as follows. So f11, meaning that if Bob receives the result j is equal to 1, then he performs the identity, so nothing on his system. So we have 0, 0 plus 1, 1. Right? So if Alice says my outcome was 1, then Bob says, okay, I do nothing. However, if Bob receives 2, then what Alice does, what Bob does, he flips his qubit. Okay, it's also unitary transformation. So this is the identity, and this is simply a flip of his qubit. So note that fj1 is unitary. So then the total LOCC operation is then described by the following. So we have E LOCC of the state psi is then sum over J. Then we have identity tensor Fj1. So this is what Bob does, and Alice performs Ej tensor identity on the state psi. And then we have Ej dagger identity, and then identity tensor Fj1 dagger. Okay, so this is the LOCC operation. Let's go through it again. So what first happens is that Alice performs on her system a operation described by these operation elements Ej. So these ones are here, right? And then she sends via classical communication the outcome to Bob, who then chooses one of these two unitaries, so either F11 or F21, depending on this outcome. So these Fj1s, right? And then the protocol is over. So that's the whole thing. And now let's calculate what's coming out. Okay. So what we aim for is that we wanna get the state phi here. We wanna see that we get this state phi via this LOCC protocol. So let's see that this is true. So to calculate the outcome, consider the following. So let's calculate this term here, this term for j is equal to 1. So we have then identity tensor F11, and then Ej, so which is E1 tensor identity acting on the state psi. Okay. So let's write this down as follows. We have E1 tensor F11 acting on the state 1 over square root of 2, 0, 0, plus 1, 1. Okay. Now we know that F11 is simply the identity. Okay, this is what we use. And we use E1 as written down here. So what E1 does, it projects on 0 and gives this value square root lambda 1. It projects on 1, gives the value square root lambda 2. And this is the identity. Remember, so we have 1 over square root of 2. And then for 0, we get square root of lambda 1, 0, 0, plus square root of lambda 2, 1, 1. Okay, and this is equal to the state phi. So 1 over square root of 2 times the state phi. Okay? And now we do the same thing for the second term if j is equal to 2. Then we have identity tensor F2, 1, and 1 tensor E2 on psi is equal to E2 tensor F2, 1, 1 over square root of 2, and then 0, 0, plus 1, 1. So let's write this a different way. So we have E2 acting on 0 and F21, which was the Pauli X operator. So we have X0 plus E2 acting on 1 and X on 1. So what is E2 acting on 0? If E2 acts on 0, this thing vanishes and we get square root of lambda 2, 1. Okay? So this gives square root of lambda 2, 1. And then if here we have x acting on 0, this flips the gate, so we have 1, 1. Now if E2 acts on 1, then this thing vanishes, and we have square root of lambda 1, 0. So then square root of lambda 1, 0, and then again here's the x gate, which gives again a 0. And this is again 1 over square root of 2 times phi. Okay? Now we can plug these things in here and get the outcome of our LOCC operation. So by using this, this is 3192, and this is 3191. Using this in 3190, we find that the LOCC operation on psi is equal to, so the first term gives us 1/2 phi phi. Okay, so this is here the first term. And the second term is here, also gives us 1/2 phi phi, which is equal to phi. And this is what we wanted to show. So we just seen that with this LOCC protocol, we can transform this maximally entangled state, so the Bell state psi, into this state phi, right? And we left these lambdas open. And since this is in a Schmidt form, and since we left these lambdas open, together with local unitaries, we've seen that we can transform this Bell state into any other state of 2 qubits. So since lambda 1 and lambda 2 were not specified, together with local unitaries, together with local unitaries, we see that we can transform the state psi into any other 2-qubit state. And we see that psi can be transformed into any other pure 2-qubit state. With certainty. Okay, so this finishes now our example. And we are continuing now with the quantification of entanglement. Okay, so what we've seen now with this, with the previous theorem, is we found a condition for bipartite pure states, which tells us whether we can transform one state via LOCC to another state, right? And we also know that any quantifier of entanglement must be non-increasing under LOCC transformations. And in particular, what we now continue are so-called entanglement monotones. And entanglement monotones are those functions which are non-increasing under LOCC operations, right? And in order then to get an entanglement measure, an entanglement measure then has to fulfill further properties, right? But those measures which are non-increasing under LOCC operation are entanglement monotones. So we start now with defining an entanglement monotone, and then we go into this direction of quantifying entanglement and finding entanglement measures. So this is the next section is 3.4.3, our entanglement monotones. So I start right away with the definition, which is simply what I just said, namely a function. Let's call this function M, which takes a state from the Hilbert space, and we get a real number as outcome, and this one is said to be an entanglement monotone. If it is non-increasing under LOCC operations. So if you study entanglement theory in more detail, you will find that there's also strong monotonicity. So meaning that they are non-increasing on average under LOCC transformation, but for us, since we are just doing a brief introduction, it suffices to define entanglement monotones in this way, right? So, but I want to warn you that if you go into the literature, you will possibly see a definition of entanglement monotones in a way that it is non-increasing on average. However, for us, and this on average is usually also sometimes called the strong monotonicity, and here we simply suffice with considering or defining a entanglement monotone in this way that it's simply non-increasing, right? Meaning that if you have a state rho, if you transform it via LOCC and get, then you know that this state which you transformed must have a lower amount of entanglement than the previous state. Lower, as small or equal, must. And now let's come back briefly to the case that we just studied, namely the case of bipartite pure states, right? For bipartite pure states, we've seen that deciding whether we can transform one state to another can be done via this vector of the squared Schmidt coefficients. And meaning that if you're interested in entanglement monotones for bipartite pure states, it might be a good idea to consider as an argument of this function this vector of squared Schmidt coefficients, right? And since we're going to do this, I now like to define what a Schur concave function is, and you will see in a second why we define Schur concavity. So let's define it first. Definition 3.24. So a function M, now from the real numbers of dimension d to the real numbers, is called Schur concave if m of x is greater or equal m of y for all x, y element of these real numbers satisfying that x is majorized by y. Okay, so now you see in which direction it goes. So before we've seen that if this vector of squared Schmidt coefficients lambda psi is majorized by lambda phi, then we can transform psi to phi via LOCC. And now this one says that this function m is called Schur concave, meaning that this one is greater or equal to that one if x is majorized by y. Okay? And this tells us that such functions, which are Schur concave, can be considered as an entanglement monotone for bipartite pure states. So let's write down some remarks here. The first thing is that any entanglement measure must be an entanglement monotone. The reason is that if you want to measure entanglement, you better be sure that it's not increasing under LOCC operations, right? So if we say that something is an entanglement measure, it must be an entanglement monotone. Then the second remark is that entanglement monotones must satisfy the following. So they satisfy that m of rho is equal to m of sigma if rho and sigma are local unitarily equivalent. Well, this directly follows from the fact that by local unitary transformations, I don't change the entanglement. And since the entanglement monotone is non-increasing under LOCC, I can go from this direction to that and back. And in all cases, entanglement is not allowed to increase. And so does the entanglement monotone. So entanglement monotone is also not allowed to increase, meaning that it must be equal for local unitarily equivalent states. Okay, so this directly follows from this definition. And then third remark, any entanglement monotone for bipartite pure states must be Schur concave and conversely a Schur concave function provides Schur concave function provides an entanglement monotone for bipartite pure states. And now you see why you see this connection between these two definitions, right? That once we've got a Schur-concave function, we can use it as an entanglement monotone for bipartite pure states. Now, as a further consequence of these definitions, is our last remark, saying that if psi can be transformed into phi via LOCC, then a Schur-concave function, so let's write down if psi can be transformed into phi via LOCC. This means that this vector psi lambda phi is majorized by the vector lambda phi. Then by the second definition for a Schur-concave function, then a Schur-concave function, satisfies that m of lambda psi is greater or equal to m Schur-concave function m. Okay, so this fourth remark now directly connects this definition of Schur-concave function with the entanglement monotones, right? Because we know that if I can transform psi to psi via LOCC, then this must be non-increasing. So entanglement cannot increase, and it happens that those Schur-concave functions satisfy this, meaning that we can use these Schur-concave functions as an entanglement monotone. However, what we do not know so far is how we can decide whether such a function is Schur-concave. Okay, and this is going to be the next theorem. So it's theorem 3.26, which tells us how we can decide whether a function is a Schur-concave function. So a function, call it M again, from Rn to R is Schur-concave if and only if it is symmetric, it is symmetric under permutations of its arguments So of its arguments, the arguments are lambda 1 to lambda d. And lambda 1 minus lambda 2 times the derivative of dm to d lambda 1 minus dm by d lambda 2 is smaller or equal to 0. The proof is going to be an exercise for you. So think about it for a bit. If this is smaller or equal to 0, means that one of these two factors must be positive, the other one negative, right? So suppose that this left one is positive, so you can assume without loss of generality, because we assume this function to be symmetric under permutations. So we can assume without loss of generality that lambda 1 is greater to lambda 2, so this one is greater to 0. Or greater equal to 0, right? And then this one must be smaller or equal to 0, meaning that the change of m by changing lambda 1 must be smaller than the change of m by changing lambda 2. Okay, and now if you connect this with how we defined, if you connect this with the theorem, which tells us that we can transform from psi to phi via LOCC if this vector lambda psi is majorized by lambda phi, then you directly see that this y is defined like this. Okay, so think about it for a bit more, and otherwise do the proof by your own at home. Well, with this we kind of have almost all ingredients together, so at least for bipartite pure states. So we know how to transform bipartite pure states via LOCC and under which conditions we can transform them. And we know now, so we define now an entanglement monotone as being a function which is non-increasing under LOCC transformations. And with this theorem, we've now found a way how we can decide whether a function is an entanglement monotone. Okay? With all of this together, we can now see how entanglement monotones look like. So we can come up with our first entanglement monotone, and we can also now come up with additional properties which an entanglement quantifier, so an entanglement measure, has to satisfy. Okay? That's the next thing what we're going to do. So the next thing is we state additional properties of an entanglement quantifier. So this is section 3.4.4. We just discuss some entanglement monotones. And measures. So, as I told you already before, an entanglement measure must be an entanglement monotone, and I also said that an entanglement measure also has to satisfy some more properties, right? And while the whole list of properties that an entanglement measure must satisfy is still more or less under debate in the community. So there's no total agreement so far, at least to the best of my knowledge, no perfect agreement so far on the whole list of the properties of an entanglement measure. However, there are at least some properties which are unambitious, which the people agree upon, right? And we're gonna list those, and we define now an entanglement measure with those properties that we are kind of sure upon which this entanglement measure must satisfy. However, I want to warn you, if you go into the literature, you possibly find also some other criterions of an entanglement measure. Okay, so let me write this down. So while there is no agreement, or there's no final agreement upon the complete list of axioms for potential entanglement measures. We here define entanglement measures via the following axioms. So the first one, okay, let's write this down as a definition. So definition 3.25 says that a function from the Hilbert space, so let's call this E, from the Hilbert space to the real numbers, is called an entanglement measure if it satisfies the following properties. Well, the first property we already know, right? It's monotonicity. So, first property is monotonicity. Meaning that E must be a monotone or an entanglement monotone. Then second is the so-called convexity, namely E of P times rho plus 1 minus P times sigma must be smaller or equal to P times E of rho plus 1 minus P E of sigma for all rho and sigma element of this Hilbert space, HA tensor HB, and P probabilities, which are between 0 and 1. Well, convexity, I think you already know convexity. And what it tells us here is that the amount of entanglement of such a ensemble, which we connect by this classical probability P, must be smaller or equal to the sum of the individual entanglement must be smaller or equal to the amount of the individual entanglement weighted by these probabilities. Okay, so this is an intuitive assumption that this must hold, because if I have the state rho and sigma, right, then in say E of rho is the entanglement of rho and E of sigma is the entanglement of sigma. If I combine them in this way, and if I say instead I have this classical mixture of the state rho and sigma, then I must suppose that this classical combination of rho and sigma cannot have more entanglement than the individual entanglement. Right? So see this argument as you've given two states, rho and sigma, from which you know the entanglement, and if you combine them into a classical mixture, and so into an ensemble, then you cannot have generated entanglement, right? Because you've combined them to a classical mixture. There's no entanglement that you introduced it. And that's why this must be small or equal to that one. Because by combining it into a classical ensemble, you do not generate entanglement. So the third is the additivity. And it says that the entanglement of rho tensor n, meaning that you take n times the state rho, right? And tensor n meaning that those rows, they are not correlated. And then this must be n times the entanglement of rho. So take n copies of rho, then the entanglement of n copies of rho must be n times the entanglement of rho. That's what it says. Okay, so it's also clear that this must hold. So this must hold for all rho. So this must be density operators. So rho element of the density operators in HA, HB. And then we also have a fourth property which must hold as the subadditivity. Which says that the entanglement of rho tensor sigma must be smaller or equal to the entanglement of rho plus the entanglement of sigma for all rho sigma being density operators on H, A, HB. And again, here you can see it such that you have two completely uncorrelated states, rho and sigma, right? And if you put them together, then the entanglement cannot be greater than the entanglement of the individual states because they're completely uncorrelated, right? Otherwise, you would have created entanglement from nothing. Okay, so these are the four properties that we require for an entanglement measure. And as I said, there are, in the literature, you possibly find some more. And we're gonna consider now, so the next thing what we do is we state some entanglement measures and entanglement monotones, right? And we're gonna start with bipartite pure states because as we've seen, bipartite pure states make our life easy. And the reason is that we know how to decide whether we can transform from psi to phi, if psi and phi are bipartite pure states. And we also know how to decide, or how to check even whether such a measure is an entanglement monotone. So it is easy to check the first condition here, right? Because we only have to check whether it's true concave. And so let's start with bipartite pure states. So first, let us recall that for bipartite pure states, or for a bipartite pure state psi, the squared Schmidt coefficients which we encountered today several times, so we know what the squared Schmidt coefficients are. So these squared Schmidt coefficients contain lambda j of psi. They are the eigenvalues of the reduced states, so of the reduced state rho A, respectively B, which we get by tracing out B, respectively A, from psi. So remember this. If you have a bipartite pure state, and if we calculate the reduced state, say, of system A, then this reduced state, the eigenvalues of this reduced state are simply the squared Schmidt coefficients. Okay? So if you don't remember it, recall this. We did this in section 1. So compare with the equation 1.53, right? And the reduced state A, rho A, has the same eigenvalues as the reduced state rho B. Right? These eigenvalues are the squared Schmidt coefficients. With this in mind, we can now state entanglement measure, namely our first entanglement measure, which is which we define as a theorem, or which we state as a theorem. We state this now, we recall this the next time, and also prove it the next time. Okay? So for a bipartite pure state, psi the von Neumann entropy of the reduced density matrix is an entanglement measure. So we have entanglement of psi is given by the von Neumann entropy of the reduced state, rho A or rho B. Remember the definition of the von Neumann entropy. So it was minus the trace of rho A or rho B, and then we have the logarithm of rho A or B, which is nothing else but minus sum over J, so nothing else but the Shannon entropy of the eigenvalues of this reduced state. Okay? And this is called entanglement entropy or entropy of entanglement. So let me finish writing down this theorem. So it is called entanglement entropy. Or entropy of entanglement. And we're going to prove that this is indeed an entanglement measure satisfying all those properties that we stated. We're going to prove this the next time. Okay, so that's all for today. And next time we continue with proving this, and then we will also state a very common entanglement monotone and continue then with mixed states. Okay, see you next time.